Hey, welcome to our third topic in our third unit, third unit on derivatives. And today's notes are a little bit shorter than some of the rest because we're going to do one proof of a rule that we're going to learn about how to add and subtract derivatives. And then most of the rest is just going to be some examples to help solidify things. A quick reminder of some things I've been saying so far in this unit. This unit is much more about raw skills and practice, where you're going to want to get your reps in, if that analogy makes sense. Just like in say music, where you'd want to practice your scales, or in sports, where you'd want to, like if you're a basketball player, you'd want to practice your free throws over and over again. You're going to want to do the same thing here. You're going to want to do a lot of practice in this section, maybe more so than just the assignment questions. You're going to want to find a textbook somewhere. And I promise you, almost every textbook looks pretty much the exact same in terms of where it starts. You're going to find a chapter on derivatives. I've got one in front of me right now. I'm just going to read out the titles of this particular textbook. The first one's on derivatives. The second little subsection is on the power rule. The third section is on sum and difference rules. Fourth section's on the product rule. Fifth section's on the quotient rule, and this book has the sixth section on the chain rule. And pretty much all books are going to kind of go in this order. So you should be able to very much find a lot of practice questions on how to add, subtract, multiply, and divide derivatives, which is kind of where we're going next. If you look at our notes here, we're going to do adding and subtracting in this section. We're going to talk about multiplying and dividing in the next section. And then after that, we'll get to the oh so important power rule, the thing that university professor that I asked before the semester, what's the important things they got to know? He said power rule. That's the important one. So sorry, not power rule, chain rule. Power rule we learned yesterday or last lesson. So anyways, let's get to our notes here. We're going to talk about how to add and subtract derivatives. We're going to talk about operations on the derivatives. So a little bit of a reminder of our notation. Derivative notation would either be f prime x or dy over dx. Those are both two different ways that we can notate things. I prefer the dy over dx because on its own, I could say d over dx, and I could tell you that we're going to derive the function 2x to the value of 2. And this notation is nice because you actually get a chance to know what the function is right here. Whereas this first notation here, somewhere else I'd actually have to write and tell you what f of x is. So those are just the pros and cons. Here's some notation for our next rule then. We're going to talk about what would happen if you want to find the derivative of two functions that are being added to each other. And the rule basically is, well, you take the two functions and you derive them each individually, which, to be honest, I've actually already been doing in some examples. I just haven't talked about this yet, but I want to do a proof of it. So here's a proof. Let's say that you had a function f of x and you had another function g of x. Right? And let's just say together what you want to do is you want to call those, like, say, capital F of x, just to kind of label these right here. So you have two functions that you want to put together. But what we'd like to do, though, is we'd like to find the prime of this. We'd like to find the derivative. Well, the rule for the derivative is it's the limit as h approaches 0 for f of x plus h minus f of x all over h. With one big difference here, though. When we were only working with one function, we just used little f, but really the function that we're talking about is actually the capital F version now, because we're really going to be deriving a composite function which involves two pieces. Right? Well, this would be equal to, really, the f of x function is really f plus g of x. So you could say that this is the limit as h approaches 0 for f of x plus h plus g of x plus h. And then you could subtract f of x plus g of x. Right? Because remember, capital F of x is really what happens when you just add these guys together. And that's all over h. Well, then I'm going to do a little bit of clever rearranging. I'm going to rearrange this to make this the limit as h approaches 0. That's still there. But now the change is, I'm going to take the f's and put them kind of together next to each other, and the g's and put them next to each other. So this will be f of x plus h minus f of x. And then I'm going to add to that g of x plus h. And remember, this negative will actually distribute in and make it a negative g of x. So it'll give you that. And then really all of this would be over h, but I'm going to skip a step and just say that if they're both over h, I can actually separate them and independently make them both over h and find the limit of both of them kind of independently. Well, for my next rule here, I need to kind of jump down below this little section that I have written here. Hopefully you're writing smaller than me. One of our limit rules is that really for a limit of two different things, you can apply that limit to both of them individually. So what you really have then is the limit as h approaches 0 for f of x plus h minus f of x. And then you can add to that a new limit. Now I see how I've got a limit notation for both of them. And now it's of g of x plus h minus g of x over h. Well, really, this is the definition of the derivative of whatever the f function is. And this is the definition of the derivative of the g function. So if you want to find the derivative of g of x and f of x, if you want to find that derivative, really the rule is you can just derive them individually, which makes all the intuitive sense in the world. We've actually been doing that already. Let's just do an example real quick. I'm going to do them out of order here. Let's do this one right here. I mean, really what this means is derive this, and then derive this, and then derive this, and then derive this. That's what it means. And we've already been doing that. But I want to introduce to you the idea of, well, let's use Leibniz notation. And so basically what this would really mean is if you want to find the derivative of this function here, I know I'm way out of order, but I hope this is useful. Really, you can find the derivative of the 6x to the 4, and then you could subtract the derivative of the 5x to the 3, and then you could subtract the derivative of the 2x, and then you could add the derivative of 17. Right? And I'd actually really like to encourage you, get in a healthy habit of using Leibniz notation, because I think it's helpful, because this notation means you still have to derive 6x to the 4. So using the power rule, pull the 4 down in front, times it by the 6 to make it 24, and drop the exponent down to x to the 3. Now work on the next step here. Well, this notation means you still haven't yet derived the 5x to the 3, so drop the 3 down in front, times it by the 5, make it 15, and then drop the exponent down to x squared. Well, then you have to still derive the 2x. Well, 2x is a linear graph with a slope of 2. So the slope of that will always be 2. And then finally, you still also have to derive the 17, and the derivative of a straight line going from flat across at y equals 17, the slope of that is 0. I won't even bother writing that. So this is our derivative, which you could write as y prime, or you could write as dy over dx. You could write it as f prime x. All of these are notations we use, but I'm a personal fan of Leibniz notation because when you write it with this sort of formatting to it, it kind of implies that you still have to take the derivative. And as we go further on into the course, especially when you learn the chain rule or when you learn how to do integration, I find it useful because it helps let you know what you have derived and what you still have yet to derive. So anyways, I'm going to hop back here to basically the two rules then. The two rules are if you have multiple things, like if you have two different things that need to be derived, right? Then, or if you like it like this, if you have to derive something that has two pieces to it, then just derive the first one, derive the second. And then really the same rule applies if there's a negative. That same logic applies. So let's hop into our examples. I'm hoping today can be a bit of a shorter video so that you can maybe cover this one and multiplication division, or hopefully you can get some practice because you're going to want this practice. So here's how you could write it. The derivative, using Leibniz notation, of 2x to the 4 plus the square root of x really means that you can find the derivative of 2x to the 4, and then you can add to that the derivative of x square root of x. Now, here's a great example of why I love this notation, because this means here I have to derive the 2x to the 4. And hopefully you're getting better at this. This will be 8x to the 3. But over here, I need to pause on this one for a second, because this one's not as straightforward. I'm going to use the power rule, but it doesn't appear right now as though I actually have a exponent. But hopefully you'll remember that square root of x is actually x to the 1/2. So I still haven't yet derived it yet, which is the nice thing about me using this is I'm going to keep writing that derivative here while I exchange the square root of x for x to the 1/2. See how I still haven't yet derived it. I'm just using this step here to temporarily change the square root to the 1/2. This guy over here has been derived, so I'm done with him, but this one here still has not yet been derived. Right? So I'll just kind of continue writing the 8x to the 3. That isn't changing. And now I'll use the power rule right here. So the way the power rule works is you pull the exponent down in front, and then you drop the exponent by 1. Well, when you subtract 1 from 1/2, it ends up giving you negative 1/2. And there's our derivative. That's what our f prime of x is equal to. Or that's what our dy over dx is equal to. Or that's what our d over dx of, what was it, 2x to the 4 plus square root of x. That's what it's equal to. So, and then quick reminder, because sometimes it doesn't hurt to remember what we're solving for. This is a derivative. A derivative is an equation for slope. I find that so important to remind kids of what we're doing, right? Because, let's do a good example. I'm doing physics with some kids right now. And one of the formulas in physics is to find out how much current there is. And current is based on how much charge there is over time. So if you had a graph of how many charges were flowing past a certain point over time, maybe for a little while you have no charge flowing. The circuit is off. And then you turn it on. And so then the circuit, starts flowing some charge. And then slowly over time you kind of turn it down a little bit so that you add some resistance so that the current is still flowing, but maybe the amount of charge is slowing down a little bit in terms of how much charge is being flowing over time, right? So there still is some current occurring here, but the change is not so much. And then maybe it goes down or maybe it's going up again, right? And then what you could figure out is like, say, right at this moment right here, well, this would be how much current there is, right? Because right here, the amount of charge you have apparently is stagnant, right? There's no slope. There's no current here. Maybe there's no current here. Here, somehow you've reversed the current somehow, maybe, if that's allowed, right? But maybe if you get the concept here, if you were to solve for this moment in time, the slope of that would be the current. But that slope will be different there than here, which would be different there than here, which would be different there than here. So, I mean, the steeper the graph, the more current there would be. Anyways, I digress. I'm getting off topic, but keep reminding yourself what a derivative is. It is an equation for slope. All you have to do is just know what your x value is, or your t value is. So if I knew that t was equal to 1, well, then 1 might be right, here. Whereas if I was looking for when t was equal to 2, that might be right here. Well, the slope is different there. All right, let's move on. Let's do some more examples. Now, this one here is a bit more challenging because really I'm not ready to differentiate it yet. And so I want to practice using my notation to illustrate how I'm going to ask you to do the derivative of the x minus 2 over root x all squared. But I'm not really at a point that I can do that yet because of this squared sign. So maybe a good way of writing it would be to say, well, I still have yet to take the derivative. And really this means that I have to write it out next to itself twice, right? Because that's what a squared means, right? To write it next to itself. I still haven't taken a derivative yet, so I'll still write my derivative notation. And now let's FOIL this out. This is going to be x squared. And then when you times one of them together, you're going to get negative 2x over root x. You're going to get another negative 2x over root x. And then for the final one, you're going to get positive 4 over x. Hopefully I didn't lose you on that foiling. X times x is x squared. That one right there will be the positive 4 over just x. This one right here will give you negative 2x over root x. And that one right there will give you negative 2x over root x. Well, now I can use my addition and subtraction derivative rules and say, really, I'm being asked to find the derivative of x squared. I also need to find the derivative of 2x over root x. And then, really, maybe I can combine these like terms here, right? Maybe let's do that first, really, because isn't minus 2x minus another 2x, isn't that going to give me minus 4x? Why don't I save myself a little bit of time and make that a minus 4x right there. Minus 4x over root x. And then lastly, I need to find the derivative of 4 over x. So the reason why I like this notation then is that I can focus on the derivatives that I'm good at solving right away, like this guy right here, this piece right here. I can derive that. I can just turn that into 2x. The derivative symbol is now gone because I have done my deriving. The verb would be differentiation, in case you're wondering how to describe that. The action word is that you differentiated it. Okay. But like for the next section yet, I don't think I'm ready to derive yet, because boy, this guy's kind of ugly. So what we really need to focus on is, oh, actually I have 2 negatives there, don't I? I have a negative here and then a second negative here. I should really just have just a 4 here. Hopefully you see my error. I can't have a negative here and then a second one there. Okay, so let's focus on this. Really, this is x to the 1 over 1, and then you're dividing by x to the 1/2. And if you remember your exponent rules for dividing are that you subtract. So what you're really left with is 4x to the 1/2. Right? You have a full x on the top. You're dividing by a half x on the bottom. They cancel and they leave you with a half x on top. So I used this line to do my simplifying. I'll do my deriving later. I'm not quite ready to do my deriving yet. And I've got a similar concept here. I'm not really ready to derive this yet. I'm going to use this step here to remind myself that this is really minus 4x to the minus 1. Right? Because an x on the bottom of a fraction is a negative exponent. Okay, well, this is where I love the Leibniz notation. The 2x has already been derived. I'm done with it. But now when I want to do the next step, pull down the 1/2. So when you times a half by 4, it gives you 2. And then drop the exponent by 1. So when you drop the exponent by 1 from 1/2, it's now negative 1/2. And see, now that I've done my deriving or my differentiation, I don't write the d over dx notation anymore. I'll do the same thing here. Now I'm actually ready to do my derivative. So I'll pull down the minus 1, times it by the 4 to give you minus 4. And then the x now drops an exponent. And when you drop minus 1 down an exponent, you drop it down to negative 2. And there, now we have a derivative where there are no more d over dx symbols. Really, I had to take 3 derivatives. I had to take this one, and that one. One of them I did in the first step, but the other ones I did in subsequent steps. So that's why I like this notation, because it's a good way of letting you know what to derive and what not to derive. Now, there are some other ways of doing it. Some people might write it as, rather than writing d over dx with x squared, they might write it like this, x squared prime. And they write the little dash up in the corner off to the side on an angle, just to make sure that it's not the number 1. Because really, x squared, if you write a 1 there, is just kind of you saying, well, it's x squared and you have one of them, which you'd just say, well, that's just x squared. But x squared primed is actually 2x. So, I mean, honestly, that subtle little change, like sometimes they write it with like an italicized font to make a difference, but I don't like using this notation because you can see how it would lead to a lot of errors where you might forget that you have a derivative still to take, and you might just think it's to the power of 1, which I know we don't normally write things to the power of 1, but hopefully you get where I'm going here. It could be dangerous to use that, so that's why I love this Leibniz notation. So. Okay, same advice I always give. Rewatch that. Look at that again. Give me some questions. Ask me how I can help. Make notes of things you didn't get, because I don't have a lot of wait time. I'm just going to move on here because it's a video, right? I'm teaching to nobody. But make sure you ask me questions, okay? I'm not getting enough questions from students right now. And your marks are probably not going to be as high because of it. You have to learn to advocate for yourself and ask questions, get help. Find someone who can help you. So, okay, I want to do an example number 4 here, one that I did at the end of the last lesson, which is one that I said was going to be on a midterm. And I want to show you another example, just because this is such an important type of question. It's challenging. So let's give this a try. I've got a function here, and it's a quadratic. And the quadratic, I mean, I know it's got a negative exponent. It's got a negative leading coefficient. It's an upside-down quadratic, but I'm not going to take my time to draw it exactly perfect. I'm just going to say, look, here's roughly what it looks like. And now I want to find the equation of both lines that go through the point 2, 9. Well, 2, 9 is going to make 2 tangent lines. One of them is going to look roughly like this. And maybe I haven't drawn this perfectly to scale, but that's not really the end of the world. The other line is going to look something like this. Right? This is the exact same kind of question we just did the other day. The big difference now being here that, well, actually, really, there is no difference. We already knew how to take the derivative of this. I just didn't talk about the official rules for it, right? So if I ask you to find the derivative, the f prime x would be equal to 2 minus 2x. Right? That would be your derivative, right? When you derive 2x, you get 2. And when you derive x squared, you get 2x. So there's your derivative, and that's equal to your slope. However, your slope can be calculated another way. If I call this point here f of x, well, let's call it x comma f of x, right? As a coordinate point, I don't know where it's going to touch, but it's going to touch an unknown x value and an unknown y value. Then you could say that the slope is really equal to y2 minus y1 over x2 minus x1. Which means that 2 minus 2x is equal to, the function itself, f of x, was 2x minus x squared, minus 9 still. And then it's over x minus 2. So we were at this point in our last day's set of notes. Right? I'm going a lot faster than I did last time, so if you need the explanation, maybe rewatch that section. So now I'm going to multiply this up here. It's going to give me 2 minus 2x, and then we're going to FOIL in the x minus 2. And then I'm just going to change the order up. I'm going to make this minus x squared plus 2x minus 9. If I distribute this, you're going to get a negative 2x squared. You're going to get a 2x. You're going to get a plus 4x. And you're going to get a minus 4. And that'll equal negative x squared plus 2x minus 9. Bring everything to that side, just because I prefer positive leading coefficients. You'll end up with x squared. Let's see, those will cancel. End up with a minus 4x. You'll add 4 to both sides. It'll be minus 5. Let's see, that'll give you x minus 5, x plus 1. So therefore, x is 5 and 1, or minus 1. Boy, I just ripped through that. Right? I mean, boy, if you kept up with that in the amount of time that I pulled that off in, that's amazing. So, I mean, the whole point of this is please go back, rewatch that, put it on slow motion here, and make sure that you understand every single algebraic step. Okay? I mean, from here downwards, that's actually grade 11 algebra skills. But hopefully you have the ability to follow that. So now I know that x could be 5 over here, or it could be negative 1 over here where they touch, which, honestly, I mean, even for my just randomly drawn diagram, that looks pretty good. Right? So, and then I talk about my function here. So, slope was really equal to, what was the equation for it again? It was equal to 2 minus 2x. And now I know my x's. So to find my first slope, it'll be 2 minus 2 times 5, which will be negative 8. To find my second slope, it'll be 2 minus 2 times negative 1, which will be a slope of 4. So then for my first equation, y equals m1x plus b. The coordinate point I can use was it 2 and 9? Yeah, 2 and 9. So 9 goes there, 2 goes here, and let's use minus 8 for my first slope. Solve for my b value. It'll be 9 equals minus 16. Add 16 to the other side. B is 25. So therefore, one of my equations is y equals negative 8x plus 25. There's one equation. The other equation is y equals the second slope. So, I mean, I'm still going to use 9 and 2 for my y and x value, but my other slope was 4. That makes this guy an 8, so then b is 1. So my other equation is y equals 8x. No, it wasn't 8. The slope was 4. 4x plus 1. All right, like I just said a little while ago, I just plowed through those. Right? I mean, that was me going fast. But that's the whole point of this sort of virtual classroom, right? There's some advantages and disadvantages. One of the disadvantages is, yeah, you don't got a teacher right there next to you, but an advantage is, yeah, you can watch this over and over and over again, and I can compact a course into a shorter video time, especially for a question that we've done before. So, I mean, really, we've done this before. What I want to point out here is that this really means we'll take the derivative of 2x and subtract the derivative of x squared, which gives us 2 minus 2x, which, honestly, we were doing that yesterday anyway, so that's not something new, really. So, okay, last example. For this one here, it doesn't really look like it's fair to work with this yet because we've got a fraction. But I'd like to point out that I can play like a little subtle algebra trick here. I'm being asked to find the derivative of x to the 6 plus 2x to the 5 plus x squared. We're dividing that all by x to the 3. Well, I mean, here's the problem is I really can't work with this in this order. But what if I change it up here? What if I do the derivative of x to the 6 over x to the 3? Keep in mind, this x to the 3 applies to all three terms, right? And then I do the derivative of 2x to the 5 over x to the 3. And then I do the derivative of x squared over x to the 3, right? Doesn't this x to the 3 really apply? It doesn't belong to all three terms. Now, I'm not really in a place yet where I'm quite ready to apply my power rule. But, I mean, x to the 6 over x to the 3 is x squared. Oh, I hope that one rang warning bells off in your head, because it's not actually x squared. I'm trying to catch you. It's actually x to the 3. Because you might be tempted to think that 6 divided by 3 is 2, but that's not how this works. You have 6 x's on the top and 3 on the bottom. 3 out of your 6 will cancel and leave you with 3. So hopefully you noticed that when I was making that mistake on purpose. This guy right here, you could call him 2x squared, right? Because 5 minus 3 is 2. Keep in mind, I'm still writing my derivative notation because I haven't yet taken my derivative. And then this one right here is going to leave you with the derivative of 1 over x, right? Because there's actually 3 x's on the bottom and 2 on top. There's actually 1 remaining on the bottom. Well, I can take this derivative. This will give me 3x squared. And I can take this derivative. It'll give me 4x. This one right here, I may just want to keep the derivative notation for an extra line just to remind myself that that's x to the minus 1. And I mean, maybe you didn't need to do that. Maybe you were able to handle it in fewer steps, right? But the point I want to make today is to practice this Leibniz notation because it's very powerful if you learn how to do it properly. So this is actually negative 1x to the minus 2. And we've talked about that one already, right? Drop the minus 1 down in front and then drop the power by 1. When you drop the power by 1, it makes minus 2. So your final answer is to find the derivative of whatever y was with respect to x, or d of f of x with respect to x, or f prime x. I mean, all these mean the same thing. The final answer is 3x squared plus 4x. Let's just make it minus x to the minus 2. There. This is an equation which will tell you the slope at any point. Right? If you want to know the slope, you just have to tell me what the x value point is. So, and I think I've said this enough times here, but this is useful in the maths, the sciences, in economics, biology, chemistry, physics. I mean, this is what calculus is used for, is whenever you've got a graph, and let's say it's not a linear graph, because most stuff doesn't fit a linear pattern. You've got something that's going up and down and up and down. Let's say that this is AC current. AC current alternating back and forth and back and forth. And you want to try to calculate the slope at this very moment right here. Well, a derivative is an equation that can help you find that slope, so long as you know what x value you're looking to put in. Because keep in mind, the slope that it is right here is going to be different than the slope here. It's going to be different than the slope there. Right? So if calculating the slope of something, if like the, again, the current divided by time, the charge divided by time, if the charge divided by time have something purposeful, meaningful to it, like say I is charge over time, like in that physics formula, then yeah, that's where this becomes very powerful, very, very useful, especially for non-linear things, right? If you only ever had linear graphs, If the only things that ever existed that were linear graphs, well, then the slope would be really boring, because if this is the equation y equals 2x plus 4, well, the slope's always 2. That's not useful, right? And I mean, how often in life are things constant and uniform? That's not how they think things work, right? Even the stock market, I've given this example before, it goes up and down and fluctuates. So, all right, anyways, my video's at half an hour. That's about perfect. So my suggestion, you need practice. Find a textbook, find worksheets online, find a workbook, ask me, I'll get you something. But I mean, do your assignment questions, but you really should do more, because this is your chance to get a leg up on first-year calc in university, so that when your professor is asking you to do the power rule, asking you to do the sum and quotient and product and chain rules, like the meat of the course, which is where we are right now, hopefully you'll have had lots of practice. So, okay, I'm done this video here. Like always, ask me questions if you have them. We'll talk to you guys later.